Good, then I would like to welcome everybody to our, well, not mini, but rather nano workshop today on Rust verification. So we put this together in a very small amount of time. So it's not going to be a large program, but we have two, I believe, very interesting and exciting talks today that show us kind of the variety of Rust verification approaches that are currently out there. So our first speaker is Vytautas Astrauskas. Vytautas is a PhD student, the last year, final year PhD student in my group at ETH Zurich. And he has been on the Prusti project from the very beginning. And so he knows Prusti inside out, and he's going to tell us today about the project overall, the reasoning technique, the tool, and everything around it. So welcome, Vytautas, and please go ahead. We cannot hear you.
One minute.
Now I could hear that. That was fine.
Okay, so do you hear me now?
Yes.
Okay, so that was strange because I haven't changed anything except stop sharing. Do you still hear me?
Yeah, now I see the slides and I hear you. Great.
Perfect. Okay, so what I'm going to present is the Prusti project. Due to short notice, I mutably borrow slides from Alex, who's one of our collaborators. So the Prusti project is a collaboration of quite a few people. Me, Aurel, Jonas, Peter, and Federico are from ETH. Zach and Alex are from University of British Columbia, and Christoph is from Technical University of Denmark. Yeah, so to motivate the Prusti project, I would like to start with a C example. So here we have an example of a C client that takes two pointers to a list, pointer A and pointer B. It modifies the list A by pushing 42 at the end of it, and then asserts that the list B didn't change. And let's say we want to prove that this assertion always holds. So that's the functional property we would like to prove. The question is, what do we need to do to achieve this? First, we need to prove that this program doesn't crash. That is, for example, this assignment to b.len, like this access of len field of b, does not cause a memory error due to b being a null pointer or being not allocated. Another point is that we need to make sure that A and B are disjoint, which, because it could be that a verb of them is a sublist of another, or they are, for example, aliases, and then this assertion would also fail. And if we are in a concurrent setting, we would also need to guarantee that we have no data races. So, and we would like to do that modularly. So the question is, how can we give modular specification to the functionality of push and functionality of client? So one of the most prevalent way of doing this is using permission-based methodology. So the idea is that for each memory location, such as b.len, we assign a permission. And when we have an access, we check that we have a permission for this access. So if permission is allowed only, the access is allowed only if we have a permission, and having a permission guarantees that the access will succeed. Now, when we call method, since we are in model verification, we need to give the permissions that are necessary for executing that method into the method itself. It takes permissions, potentially returns the same or some different permissions. And the important property of what this permission logic gives us is framing. That means that as long as we hold the permission, underlying values of the memory locations are stable. So we know that the memory locations didn't change. And there are many examples of such logic which allows with such permission reasoning. So the most popular is separation logic. In our group, we are working with implicit dynamic frames, and there are also other linear and resource logics. So what are the ingredients which we need to actually make this proof? So first of all, we need a way of denoting access to a memory location. In implicit dynamic frames and Vyper, we do that by writing accessibility predicate, which just says the location and ACK around it. In other logics, like separation logic, it would be points to assertion. And in dynamic frames, you would write a modifies clause. And yeah, there are other ways of doing that. Another crucial component is predicates, a mechanism that allows abstracting potentially unbounded memory locations so that we can have like a permission to entire linked list. And if we have two linked lists, then we need some way of expressing disjointness between these permissions. And the last crucial ingredient is a way of going from one abstraction to another that is reshaping permissions, for example, via auxiliary annotations. So because when verifying, like when we want to do an access, we need b.len permission, but it potentially is hidden inside the predicate. So we need a way to go from the list into the field and then back. And yeah, so what is this like to use? And for that, I would like to show a demo of Vyper. So here we have, is the screen visible enough for everyone?
Yeah.
So what we have here is method append in Vyper. What it does, it takes reference to a linked list and recursively traverses till it reaches the end of a list, and then allocates a new node and appends at the end of it, and then recursively comes back. The important points here are that we take the append method takes the permission, like all the permission needs to actually operate. So it takes mutable access to the entire list and it returns it. And the key point that these auxiliary annotations I mentioned is that when we are going down over recursively, we unfold the list. That means we go from the abstracted permission into its constituent, and then when we go up, we fold it. The list itself is defined as follows in very direct way. Basically say that the list is permissions to two fields, the value field and the next pointer. And if the next pointer is not null, then we also have the continuing list. And yeah, this here is our motivational example encoded in Vyper. And we can see that Vyper successfully verifies. Not sure if it's visible for you clearly enough. It says successfully verified that the length of B didn't change. And it knows that because the append takes permissions only to A, as you can see here, and the permission to B stays around, and therefore it knows that the length of B didn't change. Where the length is defined as a recursive function, which just traverses the list and counts the elements. And yeah, just to show that this is actually doing something, if I do something wrong, it complains that yeah, the session doesn't hold.
Question: how do you ensure that A and B are not aliases?
So we have so in Viper.
There. Okay.
This conjunction in Viper, like Viper has only separating conjunction. So we have yeah, basically list of A predicate with this disjoint from list of B. And since and there is a kind of a built-in assumption that you cannot have, like if you have full permission, then you know that this thing is unique. Or basically, if the sum of permissions is more than one, then these two things are different. That is kind of the actual thing that allows the solver to prove that A and B are disjoint, and therefore, yeah, basically can. This is yeah, it's basically and for the actual len, the thing is that since I pass in only list A into the append and list B stays, that's why, and this is a function. That means it is deterministic, terminating. So it's like mathematical function that and its state fully depends on the argument and the permissions. So since list B always stays in the context, we know that its value will not change. But if I, for example, called append, or yeah, if I did just B here, then we get, it starts to complain because we lost permission to B, and therefore len of B, well, like we don't know anymore that it has the same value. Does this answer your question?
Yeah.
Well, another question.
Yep.
So, the functions like len that are pure, is there a concept of something being a specification only function, or do you have to have these framing assertions for in the specification functions?
What do you mean by specification only? I'm not sure I understand the question.
What is len of B is a function, right?
Yes.
So,
Yeah, so in Viper, we have a difference between methods. So method is something that can have side effects. And let me put them closer to each other. And functions that are like pure mathematical, and they are like we can use them for computation, like in this case, we're just calling them, but we also can use them in specification. So for example, I can say that old of len of A is equals len of A plus, like basically that, for example, the length increased. Yeah, and it verifies this. So these kind of like these functions are different from methods, is that you are not allowed to use methods in specifications, but you can use functions in specifications. Does that answer, or did you mean something different?
it partially answers it, but go on.
Okay. So yeah, that's what I wanted to show with this example. Let me go back to slides. Okay, so So how does using Viper and similar tools look at scale? So if this is the actual Viper example, and if you look at them, you can see that a lot of the verification effort goes into writing predicates, writing auxiliary annotations, and all machinery to get the proof through, which is problematic because these these advanced logic concepts are not that easy to grasp, and they require an expert to deal with them. And another thing is that these steps are mandatory. That means that you have to do this work of proving memory safety before you can do anything else. And we call this proof that basically just proves that your program is well formed, a core proof. Three key problems with this manual work is that first one is complexity. There is quite a, you need to develop a mental model to how to prove this kind of programs in these logics. Second problem is amount of work. Often the overhead is like 5x or so. You need 5 times more specification than the actual code you are aiming to verify. And also, probably the most annoying one is that you need to get all this core proof first before you can even start proving properties you really care about, which is slows down significantly.
So maybe Vytautas, if I can quickly add there, I think it's important to understand that these observations are not observations about Viper, but about separation logic proofs in general. So this is completely independent of the tool you're using. All separation logic tools have the same properties there.
Yes, exactly. Thank you for. Yeah, so very fast, or like basically any tool that uses heap will have this problem. Yeah. So let's now look at Rust. So Rust is comparatively new programming language.
Hello, question?
Yes.
Yeah, so how much of that 5x is the annotation burden versus how much is doing the proof?
Sorry, didn't hear the question clearly enough.
There's a 5x overhead. How much of that is the burden of doing the annotations? And how much of it is the proof?
So since the tool is based on the SMT solver, it basically you need, so annotations in a sense are the proof. So you like things like arithmetic equalities and other similar things are like automatically handled by SMT solver. So this is like a lot of this like it's really a large proportion of this is actually getting the memory safety, so we defining predicates and defining the like auxiliary notations. So this doesn't include like a functional specification if you care about like more advanced properties.
Perfect. Yeah, thank you.
Okay, now let's look into Rust. So Rust is an interesting programming language because it targets system. So it's a systems programming language, and it is aimed at safety first. So, for example, it comes with immutability by default. So the programmer needs to, if they want to mutate values, we need to write additional mute keyword before we can mutate. By default, all values are non-aliased, and it also has automatic memory deallocation ensured by the compiler. It also has many runtime checks and compiler checks. So, for example, the aliasing, which in Rust terminology are called borrows, checked by the compiler to be well-formed. I'll talk in more detail a bit later what exactly that means. Array bounds are checked. And also there is a large library of things like smart monitors that ensure that programmers that provide safe abstractions that check that programmers use code correctly and don't make mistakes. And since it's a systems programming language, there is also Unsafe Rust that allows temporarily disabling these properties, and there you can use more C-like features like raw pointers that are unchecked, unsafe casts, assembly, and etc. The important thing is that most of the code is written in this style, checked style, and well-behaved style. So we did a study a few years back where we scanned the Rust ecosystem, and we found that this is about 70%. And also when we compare to the previous study, we found that this actually, the percentage is increasing, and the unsafe code is the proportion of unsafe code is decreasing while the time passes. And the very important aspect of Rust is that unsafe Rust is encapsulated behind library abstractions. So really majority of users are dealing only with safe code. So what are the key features of Rust type system? So Rust has important concept in Rust type system are place expressions. For those of you who are with C, C++ background, they roughly correspond to L values in these languages. Important thing is that a place owns a memory location. So if I have X, I know that it owns a memory location behind it. And guarantees that this Rust compiler uses to make sure that it can deallocate things and so on. Important feature of Rust is that the assignments are typically destructive. So if I have assignment of y into x, then the value is moved from y into x. And if I try to assign second time, I would get a compilation error. So there is only a single owner for each memory location. There are also copy assignments, for example, for primitive values. Another very important feature of Rust is borrowing, which is creating temporary aliases of memory locations. So, for example, this creates a mutable borrow of y, and it allows to mutate y through x, so via the reference x. And once the borrow expires, I can use y again. Important thing is that while the x is used, this is called the lifetime of a borrowed reference, and y is blocked. So this lifetime is automatically found by Rust, and the y is temporarily blocked for this lifetime. So if I try to interleave the axes xy, I would get a compilation error saying that, yeah, you are not allowed to do mutation here because the value is borrowed.
So it's not possible to use x, let's say, later on in the code as a parameter to, let's say, procedure invocation or something like that?
You can pass X as a to a function call, but you need to, when the lifetime is assumed to span entire function call. And basically, the key point is that you cannot have this interleaving pattern. You can pass X to functions and so on. And I'll show that in the example in the demo. But yeah, the key point is you cannot have this alternating pattern. So only one of the places has to be active at the time. Which is leads to the key Rust guarantees that places that can be used for mutation are guaranteed to be unique. Is everything clear so far, or do you need more explanation?
It's not so clear to me. What is the scope of X? So what's the scope of this X? And
So
Y, so you get this mutable copy of Y, of alias to Y.
Mm-hmm.
Any
So,
use of X later on still within the scope? Is that then still, let's say, a temporary alias to Y, or?
okay. So the thing is that the lifetime ends when the reference becomes dead in terms of variable liveness analysis. So this is the last use of X, and that's the point where compiler says, okay, this borrow ends, and therefore Y can be used from this point on. And if I had an X use after here, then that would conflict with any use of Y that is before.
How can you statically determine the scope of X? So if I have recursive procedures and so on that I pass on X to one of the invocations and so on.
Let me come back to this once I'm back in the demo, and I can show you like more of a Rust syntax. It has, or like to simply answer for things like recursion and so on, the Rust has lifetime annotations. So you can, in similar way to generics, you can specify the lifetimes in the same place. And that's how it uses to, how user can help the compiler to determine how long the lifetime should last. I could show this in more detail once I reach again a Bruce demo. Okay, let's now look at the same example we had before, just now in Rust. So the main difference is that I changed, instead of pointers, we have mutable lists, and we still want to prove this assertion. Rust guarantees that there are no memory errors. So we know that, for example, here b.len cannot fail because references are guaranteed not to dangle. That is a guarantee by the Rust compiler. Also, the Rust compiler guarantees that these two references cannot alias. And as overall result, it also guarantees that there are no data races in Rust. And the main question we explored in the Prusty project is, can we exploit this type system for verification? So with this respect, in 2017, so already 5 years ago, we started the Prusty project. And from bird's eye view, the Prusty works as follows. We have a Rust program with specifications. We feed into Prusty. It generates Viper proof. Viper tells whether the program verifies or not. and Prousty back translates the result to the user, and then basically user can continue. This approach allows us to have expressive specifications. The important point here is that it is not required to have expressive specification, but the user can. So it depends what the user wants to prove. Similar with reduced annotation, if you want to use only that your program doesn't crash, the amount of proof needed will be minimal. If you want some complex correctness property, the proof will be significantly larger. The approach can be integrated with programmer workflows. We have IDE, plugin, and so on. And internally, Prousty is implemented as a compiler plugin, which means that we work directly with compiler representation of a program, and therefore the gap between what the compiler thinks is happening and what Prousty thinks is happening should be minimal. Okay, so what does this look like? Let me jump into code. Just before, maybe I want to answer the question that was before. So typically, what you see is what programmers typically often write is code like this. So we have this case like a reference passed in and passed out, but the full syntax is, so this is kind of what compiler infers automatically is this. And that is also like the user can write in case the compiler fails to infer. So what this annotation is, it's I'm explicitly naming the lifetime, and I'm saying that I want to get a live reference X that is alive for the lifetime A, and I return another reference that lives as long as the one that was passed in. And that's how you can handle how the compiler can understand complex patterns like recursion and so on. Basically, user using these annotations can specify like the lifetimes and so on. And there are also syntax for specifying bounds. One lifetime is longer than another and so on. So Rust has a lot of machinery for specification of lifetimes. Does this clarify question?
Yeah.
Perfect. Okay, so the example I would like to show now is a simple binary search. So what you see on the screen is sequence trait. Traits in Rust are similar to Java interfaces. And this trait defines two functions, a length of a sequence and a getter function that allows to obtain an element. Both are marked as pure. That means we are mathematical, we are side effect free, deterministic, and so on. And with requires clause, we can write a precondition that index must be in range. And now we can have a binary search function that takes a type that implements this trait sequence and does a binary search over it. By default, Prousty proves absence of panics and integer overflows. That can be disabled if someone wants to, but that's default behavior. And for this example, if it complains that my code potentially can overflow. So I can fix this by just getting the proper version, like computing mid value in a way that doesn't overflow. And now if I try to verify code, it will complain about the precondition. It doesn't know that the index I'm using in the get function is within range. That can be fixed by writing this loop invariant. And now the code verifies. So, and that's basically all annotation I need to write in order to prove that this binary search will not crash at runtime, which is pretty minimal. So this is the library, so that can be reused. And for the actual code, a single line of loop invariant is enough to prove that the code is not crashing. Sorry. If I want stronger properties, for example, I want to prove that the returned, like if when I return, when the binary search finds something and returns some, the thing that it finds is actually the correct thing. So that is the element, the index returned will be at that index we will have a searched value. And yeah, this is as simple as just writing the post condition that directly express the property. And now if I want the most complex property, that is that if the code, like if a value doesn't exist, like if the function returned none, then value doesn't exist in the sequence, then I will have a quantifier to express the actual property. Then I need a precondition that the sequence is sorted and an invariant that says that the values that I already, like outside of a range which I'm considering, the value doesn't exist. And with this, I can now prove the full functional correctness. And as you can see, the annotation overhead is comparatively small. Everything like sequences and so on are generated automatically. Yeah. Another example I would like to show is binary search. So, so here we have a binary search tree. In Rust, Rust has some types, enums, and a tree. The most natural way of defining a tree is by saying that it's either a node that contains left and right subtree, or that it's an empty. And then if we can use again pure functions to define contains function that like expresses like recursively traverses the data structure and searches for the element and says whether it's find it or not. And also express the data structure invariant that if the left child contains some value, then the current node also contains it, and the value must be like less than the current one, and the same for the right one. So as you can see, we can write these annotations quite nicely. In most cases, use like in this case, completely Rust syntax. In this case, Rust syntax plus quantifiers, and we don't have any fold and fold and other auxiliary annotations needed, even though our data structure is recursive, and in the generated Viper program, we do have all these additional auxiliary annotations. So that's And yeah, to show the can actually even mutation also works in the same way, not only for pure specifications, but also if we inserting an element, we just write the post condition in pure Rust, and it just works. We don't need to do any additional code, like any guiding of approver and so on. Any questions before I go back to the slides?
Can you show, Vytautas, can you show the Rust and the Viper, corresponding Viper side by side?
Let me think if I can do that. Whoops, sorry, if I can do that quickly. Let me see. Wait. Sorry, the Zoom things are getting into the way, and I cannot easily. Okay. Yeah, let's see where it works. So I'm using a web version of Krusty, and I actually never tested whether this works on a web version. So let's see. No, it doesn't seem to be doing what I want.
That's okay. Why don't you go ahead and come back?
Yeah, I can later maybe generate offline on locally and show if this will be still interested. Okay, let me go back to slides. Okay, so how does what is the Proust approach? So what we do, we take various types, and from them automatically generate. So we take the Rust information and automatically generate the proof ingredients for that are necessary for proving programs correct. So, for example, from types, we generate predicates and permissions. From function signatures, we generate permission, preconditions, postconditions. From compiler analysis, like lifetime analysis, we generate auxiliary annotations. And from optionally provided user specifications, we generate functional correctness. So that's the high-level approach. And this gives us that Proust itself on the user level is usable by non-experts. So the people who don't need to know now separation logic, we only need to know Rust and first order logic. That means quantifiers in most cases. So coming back to the core proof, in typical setup, writing core proof requires an expert, and these steps are mandatory. With Rust, we get all this with Proust, we get all of this generated automatically, and users only need now to optionally write functional specifications. And the abstraction we need to deal with is Rust expressions plus some minor additional elements. To get a bit deeper into how this type encoding works, so here we have list defined in Rust. If you look, that would represent, let's say this blue blob represents the memory of captured by this list, and on the right we have definition of in Viper. So we have val and next fields, and in Viper we would have accessibility predicates assigned by list predicate to these fields, and later we would have the predicate for integer and also for the recursive call, and similarly we get into automatically generate this in the Viper the either to do predicate and function predicate here. Signature encoding is also pretty straightforward. So here we have a function signature that takes two mutable linked lists. So we also model them as list predicates in Viper. And since we have a guarantee that these two references are disjoint, we just put a separating conjunction between these two lists. And in Viper, that looks as follows. So we get two references and list A separating conjunction with list B. And since these are mutable references, that is, we know that they are borrowed only for the lifetime of the function, we also return this permission back in the post condition. And if the user wants to write additional specification, it just gets conjoined to the permissions you already have. Now, there is, coming back to these more intricate lifetimes, there is an important pattern in Rust, which is reborrowing. So we have a sublist function that takes a mutable reference to a list and returns its tail, like a borrow of its tail. So visually, that can be represented as follows. So let's say this triangle represents a mutable, like represents the entire list. Then the returned thing would be a small fraction. And for the caller, important thing is that as long as this return list is usable, this part is frozen and inaccessible. So the user can freely mutate the returned reference. Once we finished working with it and expire the reference, the entire list, again becomes mutable. So the question is, what formal ingredients we can use to reason about such programs? So the problem is that we cannot explicitly specify where is that fragment, especially because we want this process to be completely automatic. So this function signature, we want to work without user writing any functional specification, like without writing any annotations, unless we want to provide functional specs. But by default, it should just work. And then the question is, if the user writes a functional specification, in what way we should write it, and how they can represent what is the combined result. So the proof ingredient which we use under the hood is the magic wand, which takes, basically specifies that if you give me something that fills in this hole, then I'll give you back a data structure with this hole filled. And yeah, then conjoined to that, the caller will also get the returned reference. And we have a novel specification technique pledges that are pure specification that can be layered on top of a magic wand that allows the user to specify how this final data structure looks. For example, if we wanted to write a specification about the length of a final linked list, we could write it as follows. So we have after expiry annotation that says the expression inside it is what will hold when the returned reference expires. So we say that the length of a list will be index plus, and this before expiry is evaluates the expression just before the reference expires. So, and it evaluates the result reference. So basically, in other words, what we say is that the length of a final list will be index plus the length of the result, like of the reference that was returned by the function. Yeah, so in terms of what we did, right. I would like to, yeah, okay, let me quickly show one more advanced thing about this. So we have here, I have a variation of a pledge, but a bit more interesting one. So typically, so the pledge I showed on the slide was after expiry, which says that basically this part, what holds when the reference expires. In Rust, since we have a guarantee that the reference eventually comes back into data structure, it is also possible to do more advanced things that, for example, wouldn't be possible in Java. For example, when we have, this is a binary, still the binary search example, and I'm returning a value of a node. And what the important thing here is, this is what the data structure properties, what the data structure will satisfy when the reference expires. But the important thing is that this data structure has a type invariant. So BST has a type invariant that things in the left subtree are strictly smaller than the value of the current node. And therefore, I am not allowed to, like the client is not allowed to assign arbitrary stuff into this reference. Because if you assign arbitrary stuff, that could break the type invariant of a data structure. And therefore, like in Rust, such functions are allowed, but they are typically annotated with unsafe keyword to signal the client that you need to be careful. It is your responsibility to use this data structure correctly, because the data structure cannot protect itself from misuse. And the pledge construct allows us to also specify in which condition, what property the expiring reference should satisfy, so that the data structure is well formed. And in this case, is basically this annotation just says that the value assigned to the reference must be still within valid range, so that it doesn't invalidate the invariant of the BST. Okay, let me go back to slides. So to summarize for the tool user, with our current process design, the effort is strictly is proportional to the how difficult properties are that are being checked. So for example, if user doesn't want to check any properties, there is 0 effort. If we want to check that the code doesn't panic, doesn't crash, or some additional things like we have additional asserts, and that we have to put some additional effort, but not much. If we have want to specify type invariants and ensure them, then we have some mild effort. And if we want full functional correctness, then yeah, it can get more complex. And this, we have is nice that there is no large part at the beginning where you need to invest just to get started, but you can, depending on how much you care, you can put effort and yeah, progress with that. So the choices can vary for different code bases depending on the needs. And for the, I actually didn't show this in the demo, but when you have like a standard library like ORD trait in the BST example is from the standard library, and you can put specification on it to effectively trust the code because it's not verified. So Prusty versus the three key problems. So we had the problem of complexity. Instead, with Prusty now we get automated construction. So non-Rust ingredients are hidden. Users are mostly seeing Rust expressions plus small things like quantifiers. Amount of work is significantly reduced. Users need to focus only on relevant properties. And instead of a lot of boilerplate, we can basically start with properties what we care about. To look into Prusty from the verification expert point of view, Prusty generates proof in a standard simple separation logic, which is different from what, for example, Rust does. It's like how it's different from like Rust because there we have a custom logic to capture Rust semantics. We chose to explore how far we can get with a simple, well-studied separation logic. Prusty automatically constructs the proof implied by the Rust type checking. And due to the fact that we use implicit dynamic frames, we can just layer the properties on top. This gives the property the following pros: that we have direct model of types. We know how to extend because there is a lot of work on extending standard separation logics, and we can reuse standard automation work like Viper to automate the proof. The cons is that we are rechecking the properties, what our compiler already proved. Although for unsafe Rust, we still would need to construct a core proof. So that's not that simple. And since we are basing ourselves on a simple separation logic, more advanced live patterns become a challenge. Okay, so now I'd like to talk shortly about some ongoing and future work. So one thing we are doing is like exploring Rust semantics. So for those of you who haven't heard about, Rust has an interpreter called Miri, which Ralph Jung adapted for checking important properties of Rust. And Rust doesn't have formal semantics yet. So the community is using Miri to basically play around and as a useful tool to like for programmers to see whether we want specific semantics or not. And I believe that Prusty could complement Miri because Miri is just an interpreter. And you need to find a good test case to illustrate the problem, like good examples. With Prusty, it's much easier to like explore things. Maybe due to interest of time, I'll just quickly mention what is here. So kind of a question which with Prusty we could explore, or like one of the undecided question is, if I move a variable, does its address change or does it stay the same? Which is kind of hard to explore with testing tools. With verifier, it's a bit easier to formalize and play around. Other work we have done so far is specifying more complex idioms like closures, iterators. We have 2021 paper on that. We started exploring unsafe Rust. The aim is to explore common idioms that appearing in the world. Since we are based on separation logic, we already have machinery needed to go into this direction. And we have a paper where we explored what is actually in the wild, what are the common idioms. Another thing we're exploring is how Prusty could interact with other tools, like testing, model checking, and so on, and yeah, evaluating Prusty on real-world data. So with that, I would like to thank you. Yeah, so the key point is that Prusty allows dramatically simplified verification by automatically generating all the boilerplate code and provides the abstraction layer that is just Rust expressions with some minor things. So thank you. If you're interested, our websites are here, and you can ask questions on our Zulip chat where we always respond. Thank you. And yeah.
Vytautas, so that
Yep.
was interesting. So we're already running very late, but I think we can take time for maybe 1 or 2 questions if there are any.
Vytautas, can you say a little bit about the unsafe code verification? In that case, do you have to more extensively annotate the unsafe code so that you get a usable Viper translation?
So unsafe code is okay. So it depends from which angle we look at unsafe code. So simplest way of looking in unsafe code is just yeah, like things like double linked list that Rust cannot like Rust type system is too restrictive for implementing data structures like double linked list because it doesn't allow cyclic references. So in that case, yes, basically the idea would be that we would need just something more hybrid between regular Rust code and standard Viper. However, since we still can generate some things, for example, in unsafe code, typically there is a mix of also safe code used. So for this parts, we can still automatically infer the core proof. Also, we have function signatures, which then tell what exactly the programmer needs to prove, and so on. So yeah, there is. So to summarize, we are getting closer to the more standard separation logic proofs, where you need to have more manual effort. But I think it still will be easy. At least in some cases, should be easier than like taking C code and verifying the same example. Does this answer your question?
Yeah, seems like. Okay, if there are no further questions, then thanks again, Vytautas.